Okay? I'll show you how each one works. Whichever one you're interested in, have a play with, or all. But let me show you how I work these lessons. I hope they work. First of all, we say, here we are compiling the LBA model. Look over here, we compile in the LNR model. Over here, we compile in the DDM model. So we first of all have to say which model. Where does this live? This is a function that does the model. I wrote this function. Other people could write more functions. We look where it is. It's in files. It's in DMC, models. You can open it. LBA _B. For those who are interested, there's a stop signal, LNR. There's a little library. I will gradually build bigger libraries. Dan, if you look in there, there's the transform element. So you could put anything you wanted in there. So this is the inside. There's that likelihood function we call. When I compile it, that means it's the likelihood for the LBA. If I compile the DDM one, it'll be the likelihood for the DDM. You don't need to look inside this function, but you're welcome to. DMC will extend and extend and extend. Many different ideas we can have, many things we can do. All right, so we run that. We'll also define a design here. I'm going to make this a little more intuitive for you now instead of R1 and S1. Let's say we had a design in which, an experiment in which the stimulus was either moving to the left or to the right, and the response was either left or right. It's just a stimulus factor with two levels. Here I define what's correct, making the response left to the stimulus left is correct, making the response right to the stimulus right is correct. You could put whatever names you wanted in there, whatever mapping you want, it would all work. Run that. We have no problem. That's good. Here are some constants. I'm going to make this model simple I can fix things if I want to, so I will. No non-decision variability, I must always do that. We'll also make S to V false, variability to false, and the mean of the false 0 and 1. That kind of forms a baseline. The mismatching accumulator has a mean of 0, the standard deviation of 1. So we'll now only vary around mean, V, true, mean. Right, we'll just move that 1. In my analogy here, it's like, fix this, you don't worry about it, you just move this around when we play. So when we move this one up, we get more accurate, less accurate, affects speed, all that stuff. Okay, so run this one. Now, later on, you can change these things and see what happens. Now, the thing you more often change here is the what goes with what. So here what we're saying is, the thing we changed from last time, B is 1. There's no possibility of bias. We're assuming an unbiased model. We're simulating and assuming that. We almost always say this one, that is that the correct accumulator differs from the incorrect accumulator, and same here. But we fixed a lot of this away. So we'll make all of that. And the important thing is when you run this, it kind of tells you what you've done. See how it prints some stuff over here? It says you've got 5 parameters. A, B, so non-decision, start point variability, threshold, the rate of the matching accumulator, the standard deviation of the accumulator, and non-decision time. And then these other things are fixed, and that's what sort of model it is. So the game of this lesson will be to vary these things and to see what it does. I make B bigger, what happens? I make B smaller, what happens, right? You get a feel for that. Let's start, now we say, let's set some values here. Let's make A1 and B equals 0. That was that case of extreme speed emphasis. Right on top of the start point. So that means sometimes you sample the start point and you almost immediately respond. So this is a speed emphasis setting. Mean V true is 1, standard deviation 0.6, all right, some numbers. We make lots of them 10,000 each. Let's just do a little bit of running and plotting here, and I'll explain this to you. Yeah, so this thing started in the state of having many panels. To get rid of that, press the broom. So we get the nice big plot. So you want to get rid of them? Yeah, get rid of them. And just do that last plot thing again, just so it's big. All right, there we go. So under these settings, what have we got? We've got this 61% correct. We've got the errors are pretty fast, faster than the corrects. I actually calculated this over here. So here what I did was, I used some R. Now you need to know some R for what I did here. But essentially I calculated the proportion correct, 61%. It's also reported automatically in the graph. I calculated the speed of the trues and the falses. The trues are the correct responses, the falses there. Notice that the false is faster than the true. This is psychologically true. If I say to you, make your decisions really fast, you'll be inaccurate, but also your mistakes will be faster than your corrects. If I say to you, be really careful, then you'll be slow and accurate, and your mistakes will be slow mistakes. I don't know, maybe Chingtai, could you explain? Just repeat that. He's too busy doing stuff. Maybe, yeah, Shin, you explain those two.
是跟你正确好反应速度有什么样的关联？如果你想要反应很快的话，就会很容易犯错。那如果你脑袋想的是你要把正确率提高到一定程度的话，你就没办法把那么多注意力放在速度上，所以会有这样的trade-off 情况发生。然后看到这个模式。 现在 run 的过程是在这些参数上的设置，去接近那样实际人会产生的状况，把它参数放进去。所以在阈值那个参数，如果你提升阈值的高度的话，就会比较像是你心里面想的，一直要提高你的正确率。所以刚好在这个模式，它会将那个参数反映出来。 那如果你心里面想的是想要反应越快越好，这时候就会在drift rate 那个参数上反映出来，所以它会在这两个参数之间不断的移动，依据你心里面想要如何去做反应。
Thank you, Nishi. So now 2, 3, 4 just changes things and you look, but. I showed you, I like to show people how to do R, but here I do it all for you in a convenience function. This will now do all those calculations. So let's raise this. So what we're saying is raise the threshold to improve accuracy and make the errors slow. Now you're running totally new data. So on average this will be true. It may not quite be true in yours, may not quite be true in mine. Let's see what happens. So we see here that the accuracy went up, but it's not plotting out. This may be some setting of the system. Like that. Oh, yeah. Okay, sure. All right. So the parameter map here, there's a question about how this thing works. So, oh, right. Okay. So this is always a confusing sort of thing. We need to tell the system what is the, think of the cases we have here. We have stimulus equals left. Alright? And we need to now say what would the rate be for the left accumulator? And what would the rate be for the right accumulator? There are two accumulators. Similarly, we have here the stimulus equals right. And we need to say what are the rates of these two accumulators? So if you're used to doing DDM, this is a little confusing, but if we're responding accurately and the stimulus is left, which of these two should have the biggest rate, left or right? So this is called the matching accumulator. Right? This is the mismatch. I will use the terms, if you see it here, true and false. This will be V dot true and V dot false. Now up here, V dot true is the left accumulator. Which of these two is V dot true down here? The right accumulator. So the matching factor is a convenience factor I create for you, which always maps the right way. If you give that map and say this is the correct thing, and you say that's factor M will always be true for the matching one, right to right, left to left. It's if you're using the DDM, you only ever have factors in the experiment. If you're using the LBA or any accumulator model, you have two accumulator factors. One is this one, left and right. This one I will call R, by default in the system, R, response. This one you typically map to B. For example, you may say the threshold is low for left. I am biased to left. So you say B equals R. That will allow you to estimate response bias, allow it to be different. Here you say V is typically matched to this M factor, match, V true equals M, and that will allow there to be a difference that way. It's really a linear model trick for mapping things to things for convenience. You can do it by code. You don't want to. This is quick and easy, but it is a conceptual, how do we set it up sort of thing. But almost always when we set up this model up here, this is where we get it up there. Almost always there's an M going against mean V. And if I want to allow response bias, there'd be an R there, but in this case I didn't allow it. This force is unbiased. In the DBM, that would be Z equals a half fixed. Z equals A on 2. Okay, now we have a mystery here as to why plot.score is not returning that because it's supposed to. This is something about the Amazon, it's something about Ask Hugo. Oh, look at the function there. So it's got at the end, it sends that back. It's sending it back as invisible. So I run this guy, and it plots it, but it doesn't print it. Well, it's got to return it, so it returns. See the value there? It's actually. No, you're right. Yeah, that's just bug. So this is just a little convenience function, but it's not being very convenient, is it? Ah, there we go. Right, so the completely meaningless thing, IQR equals... Yeah, really, I have no idea how that got in there. It's not what's meant to be in there. So let me see. Well, here, let's use this as an opportunity. So I'll show you what DMC consists of. Files. We're up at the top there. Go up to the top there. There's where we start. Go into DMC. Go into DMC plotting. Down in there somewhere, if we look, There's profile, there's plot prior, plot DMC, there's some big functions, plot growth, plot PP, ACF. Yeah, there it is, plot score. Alright, now, when I first ran DMC, all of these things were compiled. But you can change them. You can come in here and go, oh, I don't like that. Oh wait, that Heathcote guy did something really stupid. So you go TRUE like that. And then you just highlight and run. Now that function has that default state. So from now on, whenever I run it, I don't need this bit anymore, because that will be there by default. Now it gives me the answer I wanted. Sorry. But it shows you that everything in here is, we believe in open source. We believe that you should never trust. You use SPSS. Yeah? What do? They don't tell you. You can't know what they do. They can do it. We can't base our science on things for other people. We must check. This is open source. It means you can come in and change, check. You find a mistake, you email me. Say you're wrong. Thank you. Fix it. Yeah? So everything in here is that. Now, it's very hard when you first start. You don't know how to do R. So you want convenience and ease. Matthew will have his way eventually. This will have a GUI. He wants a GUI on there. We're not there yet. It will happen. But I also want to get across here that as scientists we want to question down and have control of things. And so you can go in and look at all these. Of course, it may be very hard to understand my badly written code. Well, it gets better when these guys help me, but you know, it can be hard. But still, the principle should be that we always share our data, that we are open about our analyses, all this sort of stuff. Open source, open science. Okay. Finish the sermon now. We go back. Now, we'll probably come around and help you with this a little because it's good to do that. Or you can type IQR equals true, and we must remember to show. What the hell? IQR is in what I'll this. Anyway, what I want to show you there is if we run this thing, let's just run it all as one go now with it all working. So we simulate 20,000 data points, 10,000 in each condition, where now we have moved V up. We have made you more cautious. So what's going to happen? Well, actually, let's just start right back up here. Let's go. First of all, we do the one here where you are speed emphasis. So, and what I'm going to do is also clean the plots. So we start from this, start from nothing. So we run this one. Also run this. I just want to get us blank canvas. Run the first one. This is the speed emphasis condition. My errors are faster than my corrects. I'm quite fast overall, 0.6 seconds or so. I make lots of mistakes, 61% correct. I now go down and change my model, I get more cautious, so there's a bigger threshold. I run that. What will happen? First of all, I'm slowed down. Now 7.78 seconds. Now my errors are slower than my corrects. Now my distribution is spread out. I'm a little more accurate. Not much, a little more. Okay. Now you understand what the threshold does. You can learn what the threshold does by doing this. So now you can learn all parameters. Here, lowering the start point noise has similar effects. Now I take A down to 0.25. I choose some nice values here that make the lesson work well. You can play around with it. Warning, sometimes if you set the parameters to funny values, you will get things that don't look like response time distributions. You'll get funny rectangular things or things with just big long tails. The model can do this. So lower start point, there's the one. The further ones are going to be all relative to case 2 here as a kind of a baseline. So I'll set everything the same. So I'll do things like increase the rate, increases accuracy and speed. Decreasing SDV true increases accuracy and creates fast errors. Increasing T0, that's interesting. Nothing to do with the choice. So all this will do is move the whole distribution up and down, won't affect accuracy. Here, will slow things down, but now we're going to make allow for non-decision variability. Oh look, hey, IQR equals true here will now do something. It won't show the inner quartile range. I don't know what it'll do. I'll have to fix that. We'll see. It'll just print out the fast. Yeah, something got deleted when I was writing the function, obviously. All right, so you can now go through, and there's lots of things to play with there. You can go to LNR if you like. If you're interested in DDM, you can go to there. How long until our break? 3:30? Was it or 3? 4:30. 4:30.
Do we have a break between now and 4:30?
Is there?
I think it would be good to have just 5 minutes to catch up.
Yeah. Well, what I can suggest is that we all. Well, what are we doing in the break? Is there food in the break? Anything like that? We're going to be here. So 4:30 is when we finish. I actually think that we should just all now play with this, and we'll come around and help. And probably in about 1/2 or so, I may stop you, and then we may do a little bit more before we finish. Okay, is that all right with everyone? So now you play with those 3 models. I think 4:30 is There's no break. So we just work through to 4:30, but everyone now has to play with models.